Hi, today we're going to continue with computer organization and we are going to cover computer arithmetics. So the outline, we've already covered number systems, we've gone through number representation and number system conversion. We have gone through actually decimal to binary, decimal to octal, and decimal to hexadecimal, and we've gone the reverse. And we've also covered binary, octal, binary, hexa, and the reverse. And we've also looked at how to do octal to hexa and hexa to octal. So today we're going to go through and look at how to represent number systems as sign numbers. So we're going to look at sign magnitude and 2's complement. Before we go through 2's complement, we're going to look at 1's complement, which is another representation of sign numbers. And we are going to look at arithmetic operations. Today we're probably just going to cover addition. So let's start with looking at sign numbers. So we must have a method to represent both positive and negative numbers in any number system, just like we do with decimal numbers. And we're going to investigate two methods for doing this. And our focus will be on binary numbers right now, and a similar development could be done for other number systems. So we're going to look at 1's and 2's complement. Now, they permit the representation of negative numbers, and 2's complement is arithmetic is actually used in computers to handle negative numbers. So first, we're going to look at obtaining the 1's complement, and that's the easiest form of getting a negation or negative numbers. To find the 1's complement of a number, all you have to do is basically flip the digit. So if we have a number just like we have right now, a binary number, and the number is 10110010, all we have to do is flip the 1 to a 0 and a 0 to a 1, and we will get the 1's complement of the number. That's all we have to do. Every 1 turn it to a 0, every 0 turn it to a 1, and we've got the 1's complement of the number. Another way to look at this is through hardware. So one way we could do this is to have 8 gates called the NOT gate. This is the simplest form of gates that we have. I know we haven't covered this yet, but the NOT gate is the simplest gate. It's simply a triangle with a bubble at the end, and this bubble is a represents the inversion. And if you actually see a bubble on its own, the bubble represents an inversion in any circuit. When you see just the bubble on its own on a line, it actually represents inversion. But a triangle with a bubble, when you see a triangle like this with a bubble, that's an inverter gate. So if we put all the 1's and the 0's that we have, which is 100101111, that's just another number we have, and we take each bit into an inverter, then what comes on the other side is the flip of that. So we have 1 comes in, gets inverted to a 0 gets inverted to a 1, a 0 gets inverted to a 1. So you see that each input comes in, it actually gets flipped to the opposite, which is a 1's complement. So in hardware, you can get the 1's complement of a number by just running every digit into an inverter or a NOT gate, and you get the 1's complement of that digit. Okay, now to get a 2's complement, what you need to do is to get the 1's complement and then add a 1 to the end of it. Well, to the least significant bit. So let's start with the binary number 10110010, and then what we do is we flip every 0 to a 1, every 1 to a 0, and achieve the ones complement, so acquire the ones complement of it. Then to the ones complement, we add a 1. So we're going to go ahead and add a 1 to the ones complement. Now here we have a 1 plus 1. If we have, this is binary numbers, and binary numbers we only have 0 and 1. Those are our 2 digits that we can achieve in binary numbers. So we know that from the number systems that we've covered, and we know the maximum we can reach in binary numbers is a 1. So if we have anything above a 1, I have to have a 0 and a carry of a 1, because I can't get more than a 1 in my number system. I go 0, 1, 0, 1. I can't get more than a 1. So if I'm going to add 1 to a 1, I actually have to have a 0 and carry of a 1. That's the maximum I can get, so I have to carry a 1. So if I'm going to add 1 to another 1, then my answer needs to be a 0 with a carry of a 1. So 0 over here with a carry of a 1 over there, because 1 plus 1 is a 0, carry 1 in binary. So that's just the simplest form of addition. We'll do addition a little bit later in the slides, but this is just a quick form of addition review, just to be able to complete this 2's complement problem. So 1 plus 1 is 0, carry 1, and then here I have this 1 plus this 0 is actually a 1, and then we just drop everything else to the end, and this would be the 2's complement problem. So that would be how to get 2's complement. So 2's complement is 1's complement plus a 1. If I wanted to achieve this in hardware, we know that this is how to achieve 1's complement. You just run the numbers through inverters to get the 1's complement. Then I would use an adder and add 1 through the adder to the 1's complement, and then I would get the 2's complement. So this is how I would do it in hardware. Now there is an alternative method to getting the 2's complement. It's much quicker. You start at the right with the least significant bit, and you write down all the digits from right to left up to and including the first 1, and then you flip everything afterwards, meaning take the 1's complement of everything after that. So here's an example. Here's the number we start with, right there. So here's my numbers all the way up to and including the first digit, the first 1. I drop everything up to and including the first 1, and then I flip everything afterwards, do the 1's complement on it. Now this number, I could have had a 1 on the first digit. That doesn't change anything. The rule remains. Drop everything up to and including the first 1, and then flip everything afterwards. So if my example was 1, 0, let's say this was my example. Let's say this was my binary number. Let's say this was my binary number. And I wanted to do the 2's complement in this alternative method. I would drop everything up to and including the first 1, which would mean it would be this first digit. Let me erase this first. So then I would drop this digit, and then I would flip everything afterwards. This is the one that I dropped, and everything would be flipped afterwards. So the rule, these these two steps don't change. I drop everything up to and including the first one, and then flip everything afterwards. Simple. To convert from ones and twos complement back to the original form, I just use the same process. Because when you think about it, if you flip something and you want to turn it back to its original form, you just flip it again, which is the same with negation. So the next way to look at negative numbers is sign magnitude. Just like we have in decimal, if I have a number in decimal and I have 159 and it's a positive number, to make it negative, I just put a negative sign and say minus 159 in base 10, right? So with sign magnitude, a sign number consists of both a sign and a magnitude information. And the sign indicates whether a number is positive or negative. And the magnitude is then the value of the number in true binary form for both the positive and the negative numbers. So the sign bit would be your leftmost bit in a sign number, which is the most significant bit. A 0 means it's a positive number, and a 1 would mean it's a negative number. Now let's look at this sign magnitude number, this number in sign magnitude, and the number is 25 base 10, which is a decimal number, and we want to see it in an 8-bit sign magnitude format. So first we'd need to figure out what 25 is in binary. So this is 25 in binary. How do we verify that? We just look like we remember from the number conversions that we did before, but because we don't want to do this the long way, we'll just put the magnitude of each digit on top of it. So this is powers of 2. So 2 to the power 0 is 1, 2 to the power 1 is 2, and so on. So 1, 2, 4, 8, 16. So you add 16 plus 4 plus 1, that gives us 25, so we know this is the correct number. So that is 25 in decimal. So clearly, our sign is a 0, and this is our magnitude, 25, so this is a positive 25 in binary, which is what that digit says up there, that number says up there. If I wanted to represent negative 25 decimal in 8-bit sign magnitude, I would represent it in the same magnitude bits, 25, but I would make my most significant bit a 1 to make it a negative number, because I have a negative sign right there. So in the sign magnitude system, the negative number has the same magnitude as the corresponding positive number, but the sign bit would be a 1. Now, in the ones complement system, here the negative numbers are the ones complement of the positive number. So if I had 25 again, base 10 in binary form, there's the number. I want to get the ones complement of it to make it negative 25. I just flip all the ones to zeros and the zeros to 1, and I have it in ones complement form. Very simple. So now I have the negative number in ones complement form. If I wanted it in twos complement, the negative numbers are the twos complement of the corresponding positive number. If I had the same number 25 in binary form, there's the number. To get the twos complement, I want it negative 25 in twos complement form. I could do the quick way that I taught you earlier. Drop the first digit up to and including the first one. Remember that. Drop every digit up to and including the first one. It just so happens the first digit was my first one, and then flip everything afterwards. So I flipped everything afterwards, and there's my twos complement in a very quick one step. So let's look at an example. So here what it's saying, and be careful what the problem is stating, is stating express the decimal number negative 39 as an 8-bit number in sign magnitude, 1's complement, and 2's complement format. So it's actually asking you to express the number. It's not asking you to convert it, it's asking you to express it. So it's already a negative number. It's just asking you to express it in that form, right? So we need to look at it as a positive number first, because it's not asking, it's asking you to express the number. So it's very important to read the language of the problem statement to understand what it's asking you to do. So the positive 39 is this value. Let's verify. There's 1, 2, 4, 8, 16, 32. So if we add these up together, that's a 32 plus a 7, that's equal to 39. So that is correct. Now we want it in a sign magnitude. This would be the negative 39 in sign magnitude. I want to express it in 1's complement, then I would flip everything from the 39 to be negative 39 in 1's complement. I want to express it in 2's complement, then I would drop everything up to and including the first 1 from the least significant onwards, and then flip everything afterwards. So now I've expressed it in 2's complement. Now if I had asked to convert the decimal number or negate the decimal number, then I would take negative 39 and make it all positive. Now let's look at the range of sign numbers. We've used 8-bit numbers since 8-bit groupings is standard in most computers and has been given a special name of a byte. And 8 bits equals 256 numbers. So for every 8 bits, you have 256 combinations. And combining 2 bytes together gives you 16 bits, which gives you the 65,536 numbers or combinations that can be represented. And as you can see, 4 bytes gives you 32 bits and a lot more combinations, as you can see here on the slide. Now, if we want to look at how many combinations you can get for n bits, so when we look at that, the total number of combinations is basically 2 to the power n. So to get the total number of combinations for n bits, you just take 2 to the power n. That gives you the number of combinations. For 2's complement sign numbers, the range of values for an n-bit number is -2 to the n minus 1 to +2 to the n minus 1 -1. If I look for 4 bits, just to see a simple example, that gives me -2 cubed to +2 cubed minus 1, which is -8 to +9. And if we consider 0 to be a positive number, so it's really even on both sides. And then this is the range for 8 bits, -128 to +127, and that would be the range for 16 bits. So you see that when we consider sign numbers, just like with decimal, we have a range, of course, negative to positive, because then your whole number range gets divided in half, because you have to consider your positive numbers and your negative numbers in that number system. Well, now let's look at addition. So we've looked at the number conversions, the number systems, the number conversions, and we've looked at sign numbers in those number systems. We basically looked at binary, and of course the other number systems can be considered the same way. But now let's look at addition for our number systems as one of our arithmetic operations. So the procedures that we have when we look at arithmetic operations, we will have procedures for addition, subtraction, multiplication, and division. And these can be performed in any number system that we have. And the procedures we learn for decimal apply to any other radix system. Whatever we've learned for decimal, we knew since we've come through kindergarten. We know it by heart. It comes to us naturally now, but we have to really consider what we do for decimal step by step to be able to apply it to the other number systems, and that's what we're going to try and go through now. Let's do decimal addition now. And here's an example. So this is two numbers added together, and we're going to do this example the way we're used to. We're going to add these two digits together from right to left as we normally do addition. And because it's decimal, we know that we're going to say 6 plus 4 is a 10, which is a 0 and a carry 1. 8 plus 3 plus 1 is a 12, which is a 2, carry 1. 6 plus 4 plus 1 is an 11, which is a 1, carry 1. And 5 plus 2 is a 7. That's easy. We do this, and these are carries, and that's the way we do it. I would like to rewrite this for you and do it a little bit differently. 6, 8, 4. And show you a little bit different way to think of these addition, because when you're starting to add in hexadecimal or octal, the way of thinking is going to be different. You're going to have to start thinking of how many do I need to roll over and do a 0 carry 1. In decimal, you have, let's say, 1 plus 8 is equal to a 9. And then when you go to 1 plus 9, we say it's equal to a 10, but in reality, it's equal to a 0 carry 1. And I need you to keep thinking that way. It's a 0 with a carry 1. When I go to a 2 plus a 9, in decimal, it's actually what? A 1 with a carry 1. It's not an 11. It's a 1 with a carry 1. So what I'm doing is I'm taking a 1 away from here, adding it to this to make this a 0. I'm taking a 1, adding it to this to make this a 0. Carry 1. And then this leftover 1 here, I'm going to put it here to make it a 1, 1. And that's the way I need you to think on these numbers, because it makes then addition of octal and hexadecimal much easier, and it's going to help when you're dealing with subtraction and multiplication, etc. in those number systems. So, thinking that way, now let's look at this 6 and the 4 over here. So I need to take this 6 all the way to 9 and roll it over. Well, 6, because I need it to go to the 9, and then 1 extra to make it a 0 carry 1. So if I take 3 out of this 4, I'll make this a 9. So this becomes a 1, this becomes a 9, right? And then if I take this away, this becomes a 0, and this really becomes a 10, so it's a 0 carry 1. Now, of course, I'm not going to be writing this on the paper, but I have to think of this. I have to imagine it in my head. So that becomes a 0 carry 1. Now, I want to do the same here, but what I want to do is, because my larger number is on the bottom, the 8, on the next two digits, so I want to take this one from up there and make this my 9. Then I want to take another one out of here, make this a 2, and I'm going to make this 9 my 10, so it's going to be, so this would be my then 0 carry 1, and then I'm left over with a 2, so the 2 goes down here. Okay, then I have the 4 and a 6 again, so that should be my 0 carry 1 like the first set of digits. But then I'm left over, so all these, right, will come down here. Make this a 0, so this will be the 0, the 1 will drop here, and I'll have a carry up there. So the idea is that I'm moving digits around to make my larger number reach the 9, and then take one extra to make it a 0 carry 1. So I'm kind of buffing up some of my numbers to make them roll over to the carry. I'm trying to reach this. I'm trying to do what I'm doing here, right here. Moving digits around so that I achieve this 1 0 thing. This rollover, this carry, 0 carry 1. And then whatever's left over comes down here. And then this would be my 7. So see, I got the same answer, right? And this mess up here has to happen in my head. Now you might ask, why am I doing this, all this mess? I know how to do this. I already know how to do this. Yes, you know how to do this in decimal, but you don't know how to do this when it comes to octal, where your maximum goes up to 7. You don't know how to do this when it's hexadecimal, when your maximum goes up to 15. So having a way to do it like this makes it much easier. And you'll see in a few minutes. Binary addition. Now binary goes up to 2, goes up to 1, 0 to 1, and then roll over at 2. Okay. So binary addition is 0 plus 0 is a 0, 0 plus 1 is a 1, 1 plus 0 is a 1, and 1 plus 1 is a 0 carry of a 1. Because 1 plus 1 is a 2. So if I have 0, 1 like this, that's a 1, that's a 2 if I do the weights. 2 to the 0, 2 to the 1. Right? So if that's a weight of a 2, that's equal to a value of a 2 in decimal. Okay. So now let's try and do an example of addition. So if I go add these two together, the first column right here, 1 plus 0 is a 1. The next column, 1 plus 0 is a 1. Now the third column, 1 plus 0 is a, and I have to say it the way I'm saying it now because that's how you're going to practice. 1 plus 0 is a 0 carry 1. Then now I'm adding 3 together. 1 plus 0 plus 1, and this is how you want to say this. 1 plus 0 plus 1 is a 2 in decimal. 2 in decimal. 2 in decimal is a 1 0 in binary. So it's a 0 carry 1. Now I have a 1 plus 1 plus 1, which is a 3 in decimal, which is equal to a 1 1 in binary, because that's what it is up here with the powers of 2. So it's a 1 carry 1. And then now, when I go here, I add these three together. So 1 plus 0 plus 1, that's another 2 in decimal, which is a 0 carry 1. 1 plus 1 plus 1 is a 3 in decimal, which is a 1 1 in binary, 1 carry 1. And then 1 plus 1 plus 0 is a 2 in decimal, which is a 0 carry 1, because that last carry up here would be just drop down. And those would be my carries. So that's addition in binary. Now let's look at octal addition. Now octal range is 0 to 7. So I go 1 plus 6 goes to 7. Now if I add 1 to the 7, I get 0 carry 1. 0 carry 1. So see, in decimal, I'd look at this as a 10, but in octal, it's a 1 0. I have to call it a 1 0. I can't say 10. 1 0 plus a 1 is a 1 1. 1 1 plus a 7 is a 0 carry 1 plus 1, so it's a 2 0. You can see 1 1 plus a 7. 1 with that 7 is a 0 carry 1. 1 plus 1 is a 2. So it's a 2 0. Okay? So let's look at an example. These are two numbers we want to add in octal. Now we're going to follow the process that I showed you earlier, which is moving numbers around to roll over and get a 0 carry 1. So the 2 plus the 5 is just a simple 7. Now with this 7, I just want to borrow a 1 from here to make this a 4. That then becomes a 0. The 7 becomes a 0 carry 1. So then that 4 drops here and I carry a 1. Then I have a 4 plus 2 plus 1, that's a 7. A 1 plus 0 is a 1. And then I get a 7 with the 3. I can borrow 1 from here, make this a 2, and then this becomes, the 7 becomes I add 1 to this, right? So that becomes a 0 carry 1, so that's, I drop the 2, and then I carry the 1, because the 1 carries over here. And then up here are my carries, and that's my final answer in octal. So this is where that borrowing to increase the larger number to make it a 0 carry 1 is where it's going to help you in things like octal and hexadecimal additions. Next time we will, next few times, we will be going over the remainder of the arithmetic operations. So we'll be covering subtraction, multiplication, and division. Obviously, the same process works with, for addition works with hexadecimal, it's no different. We will be covering floating point numbers and character codes, and then we'll start getting into Boolean algebra. So we'll cover postulates and theorems. We'll do some switching algebra. We'll do some product of sums and some product simplification using Boolean algebra and gates. And those will be the next topics. Make sure to comment. If you have any questions, let me know. And thank you for watching.